Hey guys, welcome back. In this video, we'd like to do an example. We want to find the distance between a point and a plane, and then we'll use it to actually compute something. But we're going to start off with just a theoretical setup, theoretical argument here. Let's say we have a plane pi, and let's say we have a point P that is not on the plane pi. Okay, it's not on the plane pi. So with this plane, let's assume that we know its equation. So ax plus by plus cz plus d equals 0. And let's also assume up here that we know the coordinates, obviously, of the point in question, which we'll call x1, y1, z1, as opposed to x0, y0, z0, which is going to be a point on the plane, right, in general. So the idea is exactly this. We want to, if we know this plane, then we know a normal vector for this plane, right? A, B, C, these give us a normal vector. And remember that a normal vector is always orthogonal to or perpendicular to a plane, our plane, right? This plane. So there's our n perpendicular to the plane. And by the way, I've attached this n at some point here. Where'd that point come from? Well, you can just pick some values. You can always just pick some values for, say, x and y, and then solve for the value of z, which makes this equation true. And so I'm going to call this point down here, I'm going to change its color, call this point P naught. All right, and this one's going to have coordinates. Usually you don't put equals here, but that's okay. X naught, y naught, z naught. This is just an equation of any point in the plane. So this point P naught is in our plane pi. All right, and so then to compute the distance from this point to the plane, what we want to compute then is the distance, the perpendicular distance always, right? The distance from the point perpendicularly directly to the plane itself. So this is going to be our length d right here. Usually we use capital D in this setting. And the way that we're going to do it geometrically, the idea here is that we are going to take and connect this vector here, P naught to P, and we are going to project that vector onto the normal vector. So if you then take that vector and you project it here, right? And then the shadow, look at this, the shadow that it makes, this shadow right here, is exactly the length of d. All right, so the length of this projection vector, the length of this projection is equal to the length d. That's exactly it. That's the geometry in a nutshell. And now we just need to actually do it, right? We just have to actually do it. So again, the idea is that this makes a nice little rectangle here, even though my drawing doesn't make it look like that, but we're going to pretend I can draw. And that's exactly what we want to compute. So first of all, we need to figure out what projection is this, right? So let's call this vector v. This vector v is going to be what we call, say, p naught p or pp naught, whatever. But that's it. And so we're going to project this vector v onto our normal vector, right? So then d is equal to the length of the projection of v onto n, right? So v onto n. But remember, the length of our projection is just the absolute value of our component projection. So this is another way to do it. The length of our component projection right here. All right, and so this is all we have to do. And so we just need to plug into our component projection. By the way, do you remember the equation of the component projection? It's the dot product of the two divided by the length of the one you're projecting onto, right? And so in this case, we have absolute value as well. So this is going to be the absolute value of n dotted with v over the length of n. That's the one doing all the work, right? And so this is exactly it. There's an equation for d. All right, let's put everything in context here. We need our x1, y1, z1, and our x0, y0, z0 to make our vector v. That's the hardest part here, right? Construct this vector v, because our vector a, b, c, normal vector, is given to us by the equation, if we do know the equation. All right, so let's build our vector v then. So the vector v is going to be, component-wise, it's going to be x1 minus x0, y1 minus y0, z1 minus z0. Again, our vector n is abc, and we need to dot these together. So v dotted with n, or n dotted with v, doesn't matter, right? Order doesn't matter for a dot product. As it distributes, it's going to be, I'll write it in parts here, x1 minus x0 plus b times y1 minus y0 plus c times z1 minus z0, and then on to the next one here. we can distribute this, ax1. I'm going to do this all so that we separate out the ones and the zeros, okay? So ax1 plus by1 plus cz1 minus ax naught plus by naught plus cz naught, all in parentheses. And at this point, we remember, I hope, that this number is exactly d, right? That's exactly d. It's a point in the plane dotted with a normal vector. That's exactly d. Okay? And so this whole thing becomes, this dot product becomes ax1 plus by1 plus cz1 plus d. All right? And that's the numerator. The denominator is just the length of n. And so after all this work, what we get is that our distance between our point and our plane is given by the absolute value of this dot product that we just computed. That number could be negative, of course, right? Because any of those could be negative. All divided by the length of n. Well, the length is the square root of the sum of the squares. So this is the square root a squared plus b squared plus c squared. So there you go. There's the distance formula for the distance between a point not on a plane and the plane itself when you know the normal vector of the plane and a point on the plane. All right, let's use this to solve this problem. So I want to find the distance between two planes. And those planes must be parallel or else the question doesn't make sense, right? Between the parallel planes. And I'm going to write these planes, the equations of these planes down. I've got the equations right here. So plane 1, pi 1. This one's equation is 2x minus 3y plus z equals 4. And plane 2, this one's going to be 4x minus 6y plus 2z equals 3. And first of all, you can easily check that these are parallel because the direction vectors, remember the normal vectors are like the direction vectors of the plane. This one is 2, negative 3, 1. And this one is 4, negative 6, 2. And all of the ones in plane 2 are double the ones from plane 1. So these are definitely parallel. That part's for sure. And so the picture then looks something like this. Right? I don't know which one is oriented which way here, but the planes are parallel, so they look like this. And this is the distance that we want to measure. This is the distance, right, that we want to try to find. And so to do so, what can we do? Well, we can take, say, 1 point from this one. We can take the normal vector from this one. So there's our n2, we'll say. It can be either one. But suppose this is pi 2 on the bottom. And then we can use our process that we just derived up here with any point, say p2 from this plane pi 2, and then we can just use these two to compute this, right? So what do we need? We need a point on the plane pi 1, and we need the normal vector from pi 2. Okay, does this make sense, I hope? So let's find a point. The easiest way to find a point here is to zero out the components. So if you do x equals 0, y equals 0, then for plane 1, z has to equal 4, right? Z has to equal 4. And so this means that our point P1, or P I named it, this should be P1. Our point P1 has coordinates 0, 0, 4. And our normal vector, we already know from this one, right, is going to be 4, negative 6, and then 2. And up here, look at what we have to do. We have to plug in the coordinates of the point from plane 1 into the equation for plane 2, see what happens, right? And then divide by the length of the normal vector. And that's it. That's all we have to do here. All right, so the first thing we need to do, though, before we do it is just to make sure we don't mess up, write this as 4x minus 6y plus 2z minus 3 equals 0. And then we're just going to focus on this side, right? So when this point goes in for these x1, 2, 3 right here, x1, y1, z1, becomes 4 times 0 minus 6 times 0 plus 2 times 4 minus 3, that's going to be 5. And then the length of this thing, the square root of 4 squared plus 6 squared plus 2 squared, this is going to be what, 456? And so the distance between our parallel planes here is going to be 5 over root 56. And that's all we have to do, unless I made a mistake here, but 36, 40, 50, I think it's right. All right. And so that's just by plugging into this equation. I did it very quickly, but plugging into this equation, these values that we found.